In this video, we're going to talk about electromagnetic radiation, and I want to emphasize in the video that electromagnetic radiation is treated as both a particle and a wave, right? So let me explain what I mean by particle and wave. We are saying that energy can behave like a particle and it behaves as a wave. And the reason why I'm saying this and I'm simplifying this is because it's useful when it comes to doing all these quantum mechanics equations, etc. So we're going to treat electromagnetic radiation as a particle and as a wave when we need to. So I want to explain this wave nature of electromagnetic radiation. So I'm just going to draw a simple diagram showing a wave. So a wave has what we call a crest and a trough. Hopefully I'm pronouncing those two terms correctly. And we count the number of waves per second as the frequency. Right? So that's what that term frequency means, the number of waves per second. And then there's a term called wavelength. And the wavelength would be the distance between two crests or the distance between two troughs. Right? So that's wavelength. Right? You don't need to know the definition. You just need to understand what it is. Right? So we have frequency and wavelength. And hopefully I'm pronouncing this letter correctly. This should be mu. Is it mu or nu? I'll check it back. Alright, so this is nu, right? So this is nu. Alright, so this is our letter here, nu, and that's how I'll be pronouncing it. And we're going to use one more, which is lambda. So I'm going to rewrite it. So I have nu, and this is lambda. Nu represents the frequency, and frequency is given in, well, hertz, right? Right, where hertz is a per second, right? So how many waves per second, or hertz, and wavelength is given, and I'm going to use either meters or nanometers, and we will look at the conversions later on, right? But for your reference, in past papers, they usually give you the wavelength that is needed exactly for the calculation. Right, so far we have frequency and wavelength, and we're talking about electromagnetic radiation, where electromagnetic radiation can be drawn as a diagram which shows us a spectrum. So I'm going to go to the high energy portion of the spectrum here. Once again, let's look at our electromagnetic spectrum, and I'm going to start at the high energy end of the spectrum, and I'm just going to put my gamma radiation here, right, which is the highest form of energy of electromagnetic radiation. And I believe at the other end here should be my microwaves, if I remember correctly, lowest form of energy, right? We are saying that gamma radiation, which is high energy, what does that mean in terms of frequency and wavelength? So for gamma radiation to be a strong form of energy, that means it should have a high frequency, meaning many waves per second, right? So it's going to have a high frequency. What about the wavelength? for there to be many waves per second, this means the waves have to be closer together. So that means I should have a short wavelength. And I'm also going to introduce another unit here. Before I do so, let's talk about low energy. Low energy being the opposite of high energy. This means microwaves, for example, would have a low frequency and a long wavelength. Right? So you can include the words here if looking at the symbols are confusing. So high energy, high frequency, short wavelength. And we want to talk about another concept called the wave number. So I'm just going to introduce it to you. So we have something called wavelength, and there's something called wave number, where wave number is the inverse of the wavelength. Right? It's just a mathematical expression, right? It's the inverse of the wave number. And of course, because it's the inverse, the unit is m to the minus 1, meter to the minus 1, or nanometers to the minus 1. Right? So we are saying here that we have wavelength and wave number is the inverse. So if we have a short wavelength, we're going to have a high wave number. Now, I always tend to remember it because if frequency is high, we're going to have plenty waves, right? If frequency is low, we're going to have a low number of waves. Right? So this is our electromagnetic spectrum explained in terms of high or low frequency, wavelength, wave number. What you also need to know about your electromagnetic spectrum is the different types that are found, whether high energy or low energy. So you're going to learn off the list either from microwaves to gamma radiation or vice versa. Now that we have a little better idea about electromagnetic radiation, we can now actually go on to talking about Planck's equation.